So hello everybody, welcome to the first session, and we're looking forward very much to a great last day of this conference and to all the talks that we're going to have today. We start now with an invited talk by Melanie Habouzit, I hope I spell it correctly, from the Max Planck Institute for Astronomy, which will be on the topic of black hole formation, evolution and environment at high redshift. So please start, Melanie.
Better if I unmute myself. Okay, so do you see the screen?
Yes, yes.
Okay, perfect. Yeah, thanks. Yeah, so first of all, it's a very nice meeting. I've learned a lot. I really want to say that even the posters were super high quality. So you will see on my slide, I have few references to those. I really enjoyed, looking at those. And yeah, I will try to cover different topics today, from the formation of black holes to their evolution and their environment. So quite a few topics to cover in one talk. As you can see, my background here, my talk is going to be biased to cosmological simulations. So those simulations were made to really understand galaxy evolution from high redshift to low redshift, and we will see what kind of black holes and agent they produce. Okay, so let's start. So I like starting with this cartoon that shows a redshift as a function of the mass of supermassive black holes. And you can see here below the curved black line, those are all the detection that we have so far. So it's really a full understanding of black holes. And of course, here we have different subpopulation of the black hole population. We have high redshift quasars, and I'm not going to describe those. But the fact that we observe them at redshift 6 and even higher redshift, it really means that black hole formation is happening at very high redshift, and that at least some seeds are able to grow very efficiently to power the high redshift quasars. So this is the first constraint that we have on black hole formation, although it's really, we are talking about orders of magnitude more massive black holes than the seed mass probably. And then when we go from high redshift to low redshift, we have this population of agents across cosmic time to finally end up in the local universe, where we can really see the full diversity of black holes that we have in the universe, from very massive black holes in large elliptical galaxies, all the way down to low mass black holes in low mass galaxies or even dwarf galaxies. So here it's a summary of the mass of black hole as a function of the total stellar mass of those galaxies. And I put together different observational samples. And usually in this kind of diagram, we put this scaling relation line to really show that there is coevolution between black holes and those galaxies. And what I want to show you here is this population of low mass galaxies, because they are not, they didn't evolve as much as a massive galaxy. So potentially looking at the black hole in those galaxies can provide us with the initial properties of the massive black holes. For example, their mass at high redshift or at the formation time, and also an idea of the galaxy occupation fraction, which is the number of galaxies with a black hole, and it's a proxy for the efficiency of black hole formation at high redshift. So if black hole formation is an efficient process, we would expect all galaxies to have a black hole. But if black hole formation is inefficient, probably only a few of those galaxies will have a black hole. So this is what we call the galaxy occupation fraction. Okay, so with all those constraints put together, this is what this is how we think black hole formation is actually, happening. So we have different mechanisms. Some of them are happening at very early times in the history of the universe, even before the first stars. So this is the case for the primordial black holes, for example. But we also have mechanisms that form black holes with the first galaxies, or a little bit later on in time. So for those mechanisms, and I put here only the kind of today's prevailing mechanisms, they really need those mechanisms to explain this full diversity of black holes that we know. So high redshift, but also the diversity in the local universe. This is the first thing. Those channels, those mechanisms, they are not mutually exclusive. So probably to explain what we have seen so far, it's probably a combination of those mechanisms or other mechanisms that we haven't explored yet, but it's probably a combination of those. And then what is key is that each mechanism determines the initial mass of black holes. So for example, those POP3 black holes it's light seed, and those direct collapse, it's more massive seeds. So they determine the initial mass of black holes, but also their abundance. And I think often we forget this abundance aspect. So whether you form a lot of black holes or just a few. So just to describe a little bit more, we think that black holes can start forming in mini halos at high redshift. So in those mini halos, we expect to see the first generation of stars, so those POC3 stars. We don't know the IMF of those stars, but if we have some massive star that could collapse and form black holes of a few, like 100 solar mass, or a few 1,000 maybe. So this is what we call the light seed model. So we can form potentially many of those black holes, but if they're too light and not forming in the center of the galaxies, probably they would have a hard time actually growing to form the massive black hole that we see in the center of galaxies. We think that black holes can also form in compact stellar clusters, probably of second generation stars. So we see those clusters, they're common in galaxies. So we think that this could also happen at high redshifts. And you can have runaway collisions between stars in compact clusters, forming a very massive star that can also collapse and form a massive black holes of 10 to the 3 solar mass. That's the mass that we usually quote for these mechanisms. And then we have this exciting direct collapse mechanism. So people talked a lot about these mechanisms because it's formed seeds, really large seeds. So then it's easier to explain this population of high redshift quasar. You don't have to grow your black hole by 10 order of magnitude, but only by 4. So it makes it's easier. So these mechanisms, it's predict the formation of very massive stars in atomic cooling halos. So with no metals and no molecular hydrogen, so that you really keep a high temperature of the gas and you avoid the fragmentation of the gas. So the large amount of gas is really used only to build only one massive star that can later collapse into a black hole. So all the gas is used for one single object. So that's why they are that massive. But here again, there are massive black holes, but maybe they are too rare. So this is a summary plot of a few years ago showing the number density of those direct collapse black hole as a function of redshift. And you see I put together a lot of different studies. And what we were finding is that those black holes, they are rare, but potentially they could explain the number density of high redshift quasars. Those objects are rare, so you don't need that many of those black holes. But the number density of galaxies today is about here. I hope you see my cursor. So basically, these mechanisms, it would be hard to use these mechanisms to explain the presence of black holes in all galaxies today. So that's why it's probably a combination of mechanisms. So keep in mind the abundance of the mechanisms, the abundance of black holes. Okay, so this was for black hole formations. Now, if you want to study the coevolution between black holes and their host galaxies, we need to capture a lot of nonlinear, highly nonlinear processes, and cosmological simulation are very good tools for this. So those hydro simulations, I list them on the right. There are a couple more, but so Illustris, TNG, Horizon Agent, Eagle, and Simba, so that are the main one. That were run down to redshift 0, so from high redshift to redshift 0. And the simulation, they resolve galaxies with stellar mass of 10 to the 8, 10 to the 9, to 10 to the 11, 12. So you really have a large range of galaxy stellar mass, a large range of environments, and this is good when you want to study black holes and galaxies. So the box size length of the simulation is from 100 co-moving megaparsec to 300 for the largest simulation, TNG300. And of course, with such volume, such resolution, we cannot resolve everything. So we rely on the subgrid physics of the simulation. So basically, we put by hand recipes in the code. And the subgrid physics is used for black hole physics. So for the formation of black hole. So in the simulation, we are not following the formation, the mechanism that I was explaining in the previous slides. We just instead put black holes in all galaxies, and the mass of the black holes is the same for all the black holes. So either 10 to the 4, 10 to the 5, even 10 to the 6 solar mass for the initial mass. Those black holes, they are able to grow by gas accretion. Usually it's a bond deformalism, so a variation of it, but we have different modeling in each simulation. And those black holes, they can also merge with other black holes in the simulated volume. And we will hear a lot about this. So I'm not describing anything, but there is also agent feedback in the simulation. Okay, so with this, we can compare the population of black hole that is formed and produced by the simulation. So you will see in my talk, a lot of the figures actually show many panels, and each panel is for one simulation. And here I'm showing the black hole mass as a function of the total stellar mass. Simulation is in colors. And you see the observation are with this funny shape here. So basically this funny black shape is supposed to group all the observation from this nice paper in the local universe. Okay, so at first sight, there is a broad agreement. Observation are within the observational, the observational constraints. This is good. It's mainly due to the calibration of the simulation. So of course, we want to reproduce the black hole stellar mass relation. One thing that is important to notice is that the relation has a smaller scatter in simulation. So for example, we're missing some of the broadline agent that have been observed in the local universe. We're also missing some of the most massive black holes at fixed stellar mass. So there are some discrepancy with observations. And what we wanted to understand is how is this relation actually building up with time? So for this, we looked at the median or the mean relation between black hole mass and the stellar mass of the host galaxies, and for different redshifts. So here you see in blue, it's high redshift, 5, 4, and then we're going to the local universe with the red lines. So there is a mild evolution from redshift 5 to redshift 0. It's within 1 dex of black hole mass, so it's not huge evolution. And this is actually in good agreement with observation. So we have constraints from redshift 2 to from redshift 0 to 2. So fairly local, local redshift universe. And there is a mild evolution in those constraints as well. So we're in good agreement so far. What was surprising for us to see is this. So when we look at the buildup of the relation, there is actually no consensus in the simulations. So for example, Illustris, we're at fixed stellar mass. So along this arrow, black holes are more massive at high redshift in blue than they are in the local universe in red. And you see that we find this also in Horizon Agent and in AGOR. But in the other simulation, we're finding the opposite. Black holes are more massive at low redshift than they are at high redshift. So there is no consensus in those simulations on whether black holes are more massive at high redshift. So this was a bit surprising that you can build a somewhat similar black hole population at low redshift, but differently in time from the high redshift universe. So this those differences among the simulation is really driven by the modelings of black holes and galaxies that we put in the simulation, so the subgrid modeling. So here I'm showing the same diagram again. Observations are shown in gray just to guide the eye. And here we are following 2 black holes, but 2 black holes that are matched across the TNG and the Illustris simulation. So the nice thing with those 2 simulations is that they use the same initial conditions, so that you can really have in those 2 volumes, you really have the same galaxy. So you can match all the galaxies and you can match their black holes. And because the modeling of the simulation is different, you can see how it impacts the galaxy and the black holes in those matched black holes and galaxies. Okay, so the dashed line shows the Illustris black hole. So you see that we start with a mass of 10 to the 5. So this is a seed mass. And then the seed mass in TNG is 1 order of magnitude higher. So it's 10 to the 6. And you see that in the Illustris black hole is, growing fairly efficiently. So you have those phases with efficient growth. Whereas the black hole, the same black hole in TNG 100 is actually, following this plateau. So basically the evolution is stunted, it's regulated by supernova feedback. So the black hole is not initially able to grow efficiently. This is because the supernova feedback in TNG is more efficient than it is in Illustris. So updated their supernova feedback modeling. And then you can see, okay, many things are happening. And then at the end, you have almost 1 order of magnitude differences between the mass of those black holes for the same galaxy stellar mass. So you see that really the way we model the simulation, the black hole physics and the galaxy physics really do impact the coevolution between black holes and their host galaxies. Okay, so now we were recently trying to find what kind of constraint can we use to disentangle the simulation, right? Because there is no consensus. And observational constraint, they do not go beyond redshift 2. So we need to find something at higher redshift. And the only thing that we have at higher redshift, and I think everyone agrees with me, at very high redshift, it's high redshift quasars. So this is a summary of many different observations. So they are listed, the quasar used for this figure are listed here. And this list really take from a lot of papers. So it's really, I think if you are an observer, your quasar is probably in this distribution. So it shows the 300, almost 300 quasar that have been observed so far at redshift 6 and higher. And it's really show that most of the time we're picking up bright quasars with luminosity, bolometric luminosity higher than 10 to the 46. So those, I call them bright quasars. And then we have the faint quasars. So maybe, yeah, I think a little bit below a third of the quasars that have been so far observed so far are what we can call faint quasars. So we're getting there. Yeah, so those have bolometric luminosity of 10 to the 45 to 10 to the 46. So now, and then below, of course, we have also AGN that we are not currently able to observe, to be honest, at redshift 6. And we were wondering, how is the overmassiveness, if it's even a word, overmassiveness of black hole at high redshift compared to their galaxy? How is the signal actually changing for AGN, thin quasar, or bright quasars? Okay, so yeah, this is a complicated thing, but it's basically a mass offset as a function of redshift. So basically, if a simulation is above the black line here, it means that black holes are overmassive at high redshift. So the simulation produces more massive black holes at high redshift than they are in the local universe. And if the simulation is below this line, it means that black holes are undermassive at high redshift. So you see, again, there is this discrepancy among the simulation. So this is for all the black holes in the simulation that have mass above 10 to the 6. So basically, we're looking at the bulk of the black hole population, so really all black holes. Now, if you would be only selecting in those volumes, only the bright quasars, so the most luminous object, this is what we will find. And you see that the line here, the diagnostics, actually pretty different from the full black hole population here. So basically, if we observe bright quasars, those objects, according to the simulations, those objects are really strongly biased so that you're learning something about those objects, but you're not learning something probably about the bulk of the black hole population. However, if you're observing now the faint quasars, so basically with bolometric luminosity between 10 to the 44, 5 and 46, then the signal is actually for all the simulation pretty similar to the signal for all the black hole population. So trying to characterize the faint quasar population, meaning getting their black hole mass, but also the stellar mass of their host galaxies, we may actually learn something according to the simulation about the full black hole population. And I think this is very powerful and exciting. There is a James Webb Cycle 1 program by Masafusa Onoe is leading this. So we will have eventually those observations. So this is very exciting. Just quickly, I think we can learn more from such a program. We can learn whether, so one key question, at least to me, is whether the growth of black hole is actually really exceptional, meaning that those black holes, they grow enormously, but they are in normal galaxy, but they grow enormously. Or if it's just a normal black hole grows, but the galaxy is really in such an overdensity that it's just a very massive galaxy, and the black hole at the end is not particularly, it's not growing exceptionally, but it's just in a massive galaxy. So I think this is one key question. And then maybe when we go to this faint regime, maybe the black hole mass to stellar mass ratio can actually diagnose black hole formation mechanisms. So if you have low ratios, maybe it would indicate a light seed model where we're forming light seeds, low mass seeds. But if the ratio is high, maybe we are looking more at a heavy seed model. So depending on what the observation will provide, we may answer those questions. Okay, so now what about the growth of the black holes and their environment? So you see here the same diagram, black hole mass as a function of stellar mass in the TNG 300 simulation. So it's a large simulation. We start getting, statistics at redshift 6. And this is the observation at redshift 6 also, and the simulation is at the bottom. So we're wondering, and this is the work of one of my students, that why the most massive black holes are actually the most massive one compared to, other galaxies that have similar mass, but lower mass black holes. And to make a long story short, it's really because of an enhanced number of galaxy major merger. So here you have this XC2 stellar mass that is higher for the quasar host. So basically you add a lot of galaxy mergers, and this is boost both the accretion rate, but also the number of black hole mergers. In those simulations, and maybe I should have said this before, but there is no super Eddington accretion in most of the simulations. And also black holes merge immediately after galaxy merger, which may not be the case in the real universe. Okay, so we think
still 10 minutes.
Yeah, perfect. So, like we think that actually from simulation, we think that indeed the number of, if the environment is dense, it should favor the growth of the quasars, basically. But is the environment actually denser than other regions of the universe? And we talked a lot about this. I think it's not clear. So we have fields that are overdense, but some fields are really not showing any overdensity. And I can go further. And basically, there is no consensus at the moment. And I think we have a lot of very nice talks, and there is also the poster of Sophia, so you can get your own idea about this. Okay, so how do we explain this diversity of cases? Why are quasars not all in overdense regions, or if they are, why are we not able to see the overdensity? So we use the horizon agent simulations to try to answer this question, and there is also the work of Tiago that is with zoom-in simulation, so where you really simulate with all the computational power, given massive halo. So here it's a large-scale cosmological simulation, so we have some cosmic variance diversity of environment. Okay, so we looked at the black holes with mass of 10 to the 8 or so from redshift 4 to redshift 6, and this is what we found. So sometimes you have overdense regions like this one, where you have the massive black holes, and you see you have within 2 co-moving megaparsecs, you have a lot of galaxies definitely an overdense region. But we have cases where the same mass black holes is really just having one companion galaxies, and then there is this massive cavity, maybe an overdensity, but at much larger scale. So statistically, massive black holes are in overdense regions, but you do have this variety of environment that is truly physical in the simulation. So about 10% of the black hole speed are actually underdense when you're able to see down to really faint lower mass galaxies, which may be not the case in observation at the moment. And then we investigate how is this variety of diversity of environment changing, if you have only 2 small fields. So in some case, you're missing this overdensity completely. If your redshift uncertainty is large, you're also missing the overdensity. So we quantify this in this paper. And also, if you don't have the sensitivity to detect faint galaxy, you're also, missing the surrounding galaxies. So this can impact quite strongly your ability to detect the true overdensity. James Webb, Euclid, and Roman will help hopefully to detect those galaxies, and we also quantify how this mission will improve the current state of the Earth. Of course, in the simulation, we don't have the radiation. So, it may even further suppress galaxy formation in the surrounding, and I think we talked about this already. And we do find a lot of close companions, so we expect those in the field of view of quasars, and observation are showing this already. Okay, so this was for the quasar part. I wanted to talk a little bit about the AGN in cosmological large-scale simulation. So because the AGN are actually the black holes that we see across cosmic times. So I could have shown the AGN luminosity function, but instead I'm showing the number density of those AGN as a function of redshift. And there is this paper for the Eagle simulation with the exact same figure. And here we are following the observational constraint in gray and the simulation in red. So for different luminosity of the AGN, so here it's fairly faint AGN, and you see that a simulation like Eagle is doing a good job all the way from high redshift to low redshift. A simulation like TNG is maybe overestimating the number of those faint AGN. There is different populations. And then we're looking at brighter AGN, and you see that the simulation that was doing a good job is now a little bit below the observational constraint. Some simulation also are still okay at low redshift, but definitely having more AGN at high redshift. And you can go to ever brighter AGN, so the brightest one. So you see that some simulations do not produce the brightest AGN at low redshift while we observe them. So it may be due to a strong a strong AGN feedback here. So the summary of this, it's really that there is no consensus in those simulations on the population of AGN, while they produce galaxies in good agreement with observation, they still are producing different population of AGN. And for one simulation, and it's true for all of them, but for one simulation, it's really hard to get the faint and the bright AGN right, but also the low redshift and the high redshift AGN right. So you often get one of the regime correctly, according to current observation and constraint, but not the full picture. So I think this is a key result. Looking just very quickly at the AGN population and the AGN feedback, if you look at the number of massive galaxies in the universe, so more massive than 10 to the 11 solar mass, and you're looking at how many of them have an AGN, we have those constraints here in black from observations, and we have the simulation in colors here. So we see that at high redshift, beyond redshift 3, a lot of galaxies, those massive galaxies, they still have some AGN, and it drops really quite, strongly at lower redshift. What I want to highlight here is that some simulations are very strong, have a very strong AGN feedback to really quench galaxies, and that's what we want for galaxies. But they are really quenching the AGN as well, so maybe a little bit too much. So, an AGN modeling has to capture the galaxy, right, but also the AGN population, and this is, I think, something we should look at in more detail for the next generation simulations. Okay, and just, I think I have 5 minutes or so to finish. So I wanted to say something about the future. So unfortunately, there is no smoking gun for black hole formation and evolution. So there is not a single observation that will give us, the full picture of the formation and evolution of black holes. So this is unfortunate, but it pushes us to really observe different regimes that we can combine to get the full story of black holes. So we really have, I think, to observe both bright and faint quasars, and now we are pushing for faint quasars. So I think this is great. We also have to observe bright and faint AGN across cosmic times, and missions are also going to this faint regime, even at higher redshift. But we have to observe the most massive black holes, like high redshift quasars, but also the least massive black holes, for example, in the local universe, because they provide us with information on the initial properties of black holes. So this is key as well. And we have to observe the high redshift, but also the low redshift universe for the same reasons. So really, I think the full story will come with a combination of those regimes. So I wanted to show this figure that is from a recent Nature review that is online already. So it's really the same as in my introduction, showing the redshift as a function of the mass of supermassive black holes. And the current detection are below this curved black line as before. And you really see that the upcoming mission, they will really increase significantly our capacity to find lower mass black holes, but also higher redshift black holes, and potentially higher redshift, lower mass black holes. So the two things. So really, we will have an amazing, in the next few years, decades, we will really have a lot of observations to get the full picture. So we talked about this a lot already, but we will have an increased demographics of high redshift quasars with different mission. Rosita is also, I was happy to see that it's also providing, high redshift quasars. Statistic on high redshift AGN will, at high redshift, we will have, very nice missions like Athena, really going down to fainter AGN, and so probably powered by lower mass black holes. So we're getting to this regime at high redshift. Maybe the concept mission axis and links. We are approaching the newly formed and young black holes, so this is also very cool. And I think one key thing is that we don't need to observe only the black holes, but we also need to observe the host galaxies, right? And the galaxy in general at high redshift. So James Webb, Euclid, Roman, ELT, those will help us to get the galaxy properties. So this is very cool. So just to say a few things. So Lisa, if you form a black hole here, taking a little bit of time. Okay, so if you form a black hole here, as I was explaining at the beginning, every time this black hole will grow in mass, and every time it will merge with another black hole, if the merger happens in those shaded area, you will have an ELISA event. So basically, almost all the black holes that are forming at high redshift will, at some point, if they're merging, will be, ELISA detection. So this is very powerful, and I think Flora will talk about this. And then you see all the electromagnetic missions here. I wanted to say a few things about the X-ray missions. Okay, so this is, with all the simulation that I was talking about, we can try to prepare those missions, the X-ray missions, to to understand what kind of population we are going to see. And this is a prediction for the number of agents in given surveys of Athena and then the concept mission axis and links. You cannot compare the different prediction on purpose that are using different surveys. But what you see here is that for the different cosmological simulation, there is about 1 order of magnitude difference in the number of agents. That is huge. So one comment could be, okay, you just show that the agent population are not always agreeing with current observational constraints. So why do we do this? I think when we're taking all the simulation together, and not just one, but all together, we're still getting a fair, understanding of what could be the impact of different modeling in the simulation. So a good understanding of the uncertainty that we could have with future observations. So this is also telling us that, those missions, they will have the power to constrain the simulation as well. And probably skipping this, it was just to show you how with those new X-ray missions, you will really go to this spent agent regime at high redshift, and you really are going to sample lower mass black holes. Yeah, I'm finishing. And just very quickly, one thing that is key is also looking at the low redshift universe. And I think we can keep learning a lot from the low redshift universe, and particularly low mass galaxies. So we talked a little bit about cosmic void already, but I wanted to say a few things about the local low mass galaxies. So recently we compare the black hole and agent population in the simulations again, and we find really significant discrepancy in this regime that is not calibrated in the simulations. So it's true predictions. And you see here the agent occupation fraction, so the number of galaxies that have an agent, and it's really a discrepancy of 1 or 2 orders of magnitude across the simulation. This is due to, again, the seeding, the accretion formalism that is used, the supernova feedback. So this is interesting to see that we have discrepancy there. When we compare this, and it's really to finish now, with observational constraint at the moment on this agent occupation fraction, we see that some simulation may actually produce too many agents, and this again is maybe due to too massive black hole in the simulation. So we still need to explore this regime in large-scale cosmological simulation. And I just put my summary, but I'm stopping here.
Okay, very nice. Yeah, it's a very useful and very, very insightful presentation. Many thanks, Melanie. We have already 4 questions in the Q&A, and I think we still have about 8 minutes for questions. I will now just basically activate the speakers, the people who ask questions, so that I can ask them in live. The first one is Ryan Hickox, and I will, you're now allowed to speak, Ryan. So if you could ask your question, and then Melanie can answer it.
Great, thanks, Dominic. Thanks, Melanie, for this very interesting overview. You mentioned and showed a number of plots showing the median or average values of black hole mass compared to galaxy mass as a function of redshift for the different simulations. And I was really struck by this point you made that there's no consensus really on, especially at high redshift, what that is. But I was wondering, in addition to that, of course, there's a lot of dispersion in those values. And I was wondering if we have observational constraints that we can use to actually use that dispersion to then constrain the theoretical models.
Yeah, that's a good point. So there is a dispersion. It's lower, the dispersion, the scatter is lower in those simulations compared to what we see in the local universe. So the scaling relation in simulation are really tighter. So we're missing some of this, scatter that we should probably have. I think, so it can, the fact that the scatter is smaller can come from really different things. In simulation, we are using the same modeling for all galaxies, which may not be the case. So for example, the efficiency of agent is the same for all galaxies, which, you probably expect a scatter there that could increase the scatter. I think also, spin of black holes, this is not modeled in the simulation. It can also increase the dispersion. So we're missing it's both the modeling, but also our ability to put the physics into the simulation, and the missing physics that could also play a role in this scatter. I don't think we have that many observational constraints beyond redshift 2, honestly. So really what we can try to look at is a scatter from redshift 0 to 2, but then it's very hard, at least for the black hole mass stellar mass relation, to get constrained on the scatter beyond redshift 2. Yeah.
Super. Thanks very much.
Yeah, thanks very much. Yeah, the next question is by Carla Cutiva Alvarez, and we will now also allow Carla to speak and to ask a question. Yeah, Carla, are you hearing us? Good, if she's currently not available, there's also a question by Il-Sang Yoon, and then I will also activate Il-Sang so that I don't know, he or she can ask the question also.
Hello.
Hello, yeah.
Thank you, Melanie. Yeah, it was very educational, and because I'm not in the field of galaxy formation simulations, I'm basically wondering, you mentioned about different subgrid physics create inconsistent result. And I just wanted to know more about this. Can you comment further on this? For example, are those prescriptions are totally different from each other, or can we somehow categorize them into a few distinct types so we know what physical mechanism may be a key driver of changing the black hole growth?
Yes. So yeah. So first, I would lower down a little bit. So at first sight, there's a good agreement with the black hole population and observation. But it's really if you look more carefully that the disagreements start emerging. So yeah. So I see your point. What's hard is that the physics of black holes and galaxy. You have so many degeneracy that it's hard to really understand what is doing what. So, for example, if you look at the initial growth of black holes, it's a combination of, what the initial mass that you're putting for the black hole, so the seeding mass. What is the formalisms for the accretion, the accretion of gas into the black hole? So whether you're using Bondi that depend on the square root of the black hole mass, or another modeling that maybe doesn't depend on black hole mass but more angular momentum. But also, the power of supernova feedback to really push the gas away from your galaxy. So it's really a combination of those. And also simulation, they are using, slightly different version of the modeling. So yeah, I would say it's hard. So in the papers, it's hard to describe everything in one talk. But yeah, in the paper, we try to describe this in more details and also find diagnostic that you can go to observation and try to disentangle the different modeling, but I would say the degeneracies are pretty hard there.
So okay, so just a quick follow-up. So overmassive, overmassiveness, the trends as a function of redshift to show the two distinct behavior for different simulation. So your point is that so detailed prescriptions on doesn't really matter to create those two very different behaviors. So that each different simulations doesn't share the common characteristics of the prescription. Is that correct?
So most of the spirit of the modeling is the same. So you want to have some gas accretion, you want supernova feedback, you want agent feedback, but the strength of those mechanisms is different. So for example, a simulation like Illustris, the strength of the supernova feedback was not maybe sufficient. And yeah, so the agent feedback was also a little bit displaced from the host galaxy. So this triggered more massive galaxies. So you would have this evolution in the time evolution between black hole mass and stellar mass that is driven by actually the power of galaxy to grow more than their black holes because of those reasons. So things like that.
Okay, thank you.
Okay, I think we have time for potentially a last question by Christopher Agostino, even though the answer will have to be brief, but I can briefly give you the word.
Hi, Melanie. Thanks for the great overview. So you showed that plot showing the FAGN fraction versus redshift and how the Z of approximately 0 is too high compared to the simulations. I was wondering if that was based on the SDSS BPT AGN, and if it includes like the local QSL population.
Yes, so tricky question. Yeah, so it's definitely based on the Kaufman paper from a long time ago. Yeah, so okay. Maybe there is some new constraint that we could put there. Yeah.
Okay.
Okay, very nice. Yeah, so thank you very much, Melanie, again. And yeah, we come now to the first contributed talk in this session. This will be given by Tiago Costa from the Max Planck Institute from Astrophysics in Garching, and he will talk about quasar feedback and the origin of extended Lyman alpha glow in set larger than 6 quasars. Yeah, please start, Costa.
Okay, thank you very much for the opportunity to speak to you. So I'll be presenting to you new results that touch on recent observations of extended Lyman alpha emission around the first quasars in the universe. So I'll be presenting here is a possible explanation for where these come from. I will just give you a bit of an introduction. So back in 2014, when I looked at supermassive black hole growth with cosmological simulations, one of the results that stuck out was that we were unable to explain the formation of very massive black holes with 10 to the 9 solar masses unless we really were tracing the most extreme halos in the universe of redshift 6. And when we looked at the cosmological environments of these halos, we find that they are incredibly different from normal redshift 6 regions of the universe. This is illustrated by these two images, which show you the density field of redshift 6 in an average region and around the quasar. And this environment is crucial for the growth of the quasar. What you see here is this network of cold filaments, which is falling into the quasar and provides the gas reservoir that allows these black holes to grow rapidly and for the host galaxies to form stars. Looking more closely, we also found another important ingredient of these simulations was outflows driven by the AGN. So no matter what model we put in for the AGN feedback, whether this was based on an energy-driven prescription for AGN feedback, or whether it was the outflows are driven by radiation pressure on dust, we were finding strong, large-scale outflows. So this movie shows you the cosmological environment in one of these simulations. The blue gives you the stuff which is falling in towards the quasar and traces this web of cold filaments, and the orange-red colors give you these outflows. You can see the outflows propagate into the voids while the filaments continue to fall in straight to the quasar. So these outflows are quite rich in internal structure, so they look differently depending on where you're looking at. So at small regions, you find a sort of cold component, which is then taken over by a warm ionized component, whereas at the largest regions above about 10 kiloparsecs, the outflow is dominated by low density hot gas. Now, the question is, can we, using observations, especially Lyman alpha emission observations, test these predictions of these models, and in particular, this key prediction that there should be a significant gas reservoir around these quasars. I will be comparing these simulations with recent data by Emanuele Farina, which uses MUSE observations of Lyman alpha around redshift 6 quasars. And in this sample of 31 quasars, about 12 Lyman alpha nebulae were detected. So these have a strong variation in properties, but their sizes are typically on the order of 20 to 40 kiloparsec, down to surface brightnesses of 10 to the minus 18. So our simulations are good to test this kind of observations, because we're tracing regions where we're able to form black holes of 10 to the 9 solar masses, but also because we have recently been running radiation hydrodynamic simulations that allow us to also predict the ionization state of gas at large scales as it's processed by both the stellar and the AGN radiation. And what we then did was we post-processed these simulations with a radiative transfer code for Lyman alpha radiation and investigated the main Lyman alpha mechanisms that have been proposed. So these are recombination radiation from photoionized gas, Lyman alpha, which is produced by collisions between hydrogen atoms and free electrons, and also this scenario here, which I call BLR scattering, or scattering from the broadline region, which envisages that the Lyman alpha associated to the intrinsic quasar spectrum produced in the broadline region scatters off neutral gas up to halo scales. Of course, it's the extreme of this model. Lyman alpha scatters because the absorption concentration is very high. In this scenario, the photons would be transmitted all the way from the nucleus to the halo. So I'll be testing all these scenarios. So to jump straight to the results, this picture shows you again what the cosmic density field looks close to the central quasar. So you see the host galaxy, you see these inflowing streams that I've already discussed. You also see a few satellites. And if I now plot the surface brightness of Lyman alpha as predicted by these calculations at exactly the same scale, this is what I find. I indeed find extended Lyman alpha emission. So these yellow and black contours correspond to 10 to the minus 18 and 10 to the minus 19 in surface brightness units. The typical luminosities, when you integrate over the whole image, tend to be on the order of 10 to the 44 ergs per second. This is the most luminous case we have. So this is just qualitative results. So we do get these extended Lyman alpha nebulae, but do they agree in detail with these observations? I want to say before I show you the comparison of the surface brightness, just to make the point that this Lyman alpha nebula can look completely different depending on what line of sight you take. So this is always the same system that you're looking at. It's the same quasar, the same simulation, but looking through different lines of sight. And what we were finding, which is interesting, is that sometimes, for example, if you take this panel here, the quasar is centered on the Lyman alpha nebula, which is roughly spheroidal. But in some other cases, the quasar almost looks like it's outside of the nebula. So this red cross represents the position of the quasar, and the white circle, the flux-weighted centroid of the nebula. So the viewing angle really matters a lot. Now, to go to the surface brightness comparison, these circles give you the observed median profile from the Requiem survey that I've introduced in the beginning. And these different blue lines give you different random lines of sight through our system. And what you find is that sometimes they are brighter than the observed profile, sometimes they are fainter than the observed profile. When you average out over all these lines of sight, you get this thick blue line, which is actually pretty close to the observed profile. And I found this is... Yes, this is a remarkable result because these simulations were run to test AGN feedback and not to give an accurate modeling of the CGM. So what is the mechanism for these nebulae? I first will show you what collisional excitation provides. So indeed, this generates an extended nebula. But when you compare the surface brightness with the observed one, its shape and its normalization is very different. So the nebulae are too faint if we only include collisional excitation. If we account for recombination radiation, the nebula becomes much larger and much brighter. And we actually start being able to reproduce the central regions of the surface brightness profile, but we systematically underestimated, albeit by only a factor of 2 or 3 at larger radii. And the surprise was that when we tested scattering from the broadline region, we were finding we got the strongest and largest and brightest Lyman alpha nebulae. So this shaded region gives you the range of profiles that you can get with this mechanism. This depends on how much of the AGN bolometric luminosity comes out in Lyman alpha. But you see for the low values, you touch on the lower range of the observed profile, whereas for the higher values, you even start overproducing it a bit. And what this means is that even if you just have this mechanism, it's enough already to explain both the shape and the normalization of these Lyman alpha nebulae. We also found that whether you get this nebulae or not depends extremely strongly on whether you include AGN feedback in the simulations. This is a simulation that includes AGN feedback via radiation pressure on dust. So these are the results I've been presenting to you. And this is what the nebula looks like, same viewing angle, same redshift, but in a simulation where we do not include AGN feedback. It goes away. It becomes very small and very faint. And the reason for this is that AGN feedback, as I showed you at the beginning, clears out the central regions of the galaxy and allows the Lyman alpha photons produced both by photoionized gas and by the quasar broadline region directly, allows these photons to escape and still scatter and be in resonance with neutral hydrogen in the halo. If you do not have AGN feedback, you have an extremely optically thick central galaxy. The photons are redshifted and blue shifted, and once they escape the central region, they're no longer scattering. This is shown in this plot that gives you the radius of last scattering the photons without quasar feedback and with quasar feedback. And you see that the region where these photons stop scattering is extremely different, very small without quasar feedback and out to hundreds of kiloparsecs with quasar feedback. And the final result I want to show you is that we've also tried looking at redshift 7.5, the most distant quasars, and we find that we would expect also these sources to show evidence of bright Lyman alpha nebulae. So I show you now, give you just the conclusions. Thank you.
Yeah, very many thanks. Very, very nice results. We have one question from Michael Strauss, and I will give him very quickly the word, and then we'll have to continue with the next speaker. Moment. Yeah, with a long list of participants. Now, Michael, please speak.
Thank you. Michael Strauss here. So can you also make predictions about continuum light? Do we expect to see scattered continuum light? And are there any other emission lines I assume no other lines are resonant enough to give you extended emission.
So we have made predictions also for H alpha and helium-2, because these are non-resonant or scatter less efficiently. They tend to be much more compact. So that would be actually a way to test these simulations.
Yes.
To compare the surface brightness profiles of these lines.
How about continuum?
This we haven't modeled. Yeah.
That
would be quite interesting. Thank you.
Okay.
Yeah, many thanks. Yeah, there are more questions in Q&A, but we have to, I mean, they can be answered in Slack. And we continue with our next speaker. This will be Laura Blecha from the University of Florida. And she will talk about multi-scale modeling of supermassive black hole evolution and gravitational wave sources. And yeah, you're connected. Yeah, please speak, Laura.
All right, thanks very much, Dominic. It's great to be here for this really great conference. I've been enjoying it all week. And I also want to say special thanks to Melanie for giving a great introduction to cosmological simulations, which makes it much easier for me to cover several things in this 8-minute talk. So I'm going to highlight a couple of things that my group has been working on recently regarding the modeling of supermassive black hole evolution in cosmological and galactic scale simulations. So there's, as we've been learning at this conference, there's a lot of different aspects of black hole evolution that go into galaxy evolution and conversely into producing gravitational wave and multi-messenger sources from black holes. So yes, I'll be focusing on the simulations aspect of this, but I made this little diagram. And I just want to highlight that I'm not going to talk much about the supermassive black hole formation angle. We'll have a talk by Annalise Evans, a graduate student in my group, in the next session, and also a poster presentation by Ankwan Bomek later today that will talk about some of the exciting stuff that they're doing regarding black hole seeding. So in this talk, I'm going to focus on two different aspects of black hole dynamics. The first is the dynamics of the local ISM and how that impacts black hole fueling, and then also the dynamics of multiple black hole systems. So to start with, one of my graduate students, Anish Savasankaran, has been conducting a suite of simulations of black hole fueling using the SMUGGLE ISM model, so a model for an explicit multi-phase interstellar medium, in contrast to the effective equation of state models that are used in many of the simulations that we've been talking about thus far, especially the larger volume cosmological simulations. And so increasingly there are a few different models. The FIRE models is another example, where the collapse of gas clouds down to high densities and cold temperatures is being modeled directly, and stellar feedback is injected locally. And so you can see here just sort of schematically the difference this makes in the density of the ISM in an isolated galactic disk, and also the difference it makes in the black hole accretion rate. So this is the orange line here, the effective equation of state model, and then we see a similar average but wildly fluctuating accretion rate that's entirely driven by the stellar feedback blowing bubbles locally in the disk here. And so Anish has been implementing this in isolated and merging galaxy simulations. So this is just a nice image of one of these galaxy mergers. There's also super Lagrangian grid refinement scheme, so we get extra resolution around the black holes. And so this work is going to be submitted very soon. And one of the key takeaways is that galaxy mergers do drive inflows that enhance accretion, but the AGN duty cycles that the actual instantaneous accretion rate is entirely determined by the local ISM. Right, so the second thing I wanted to talk about is the formation of supermassive black hole multiples so the binaries and also triples in particular. So this builds on this suite of binary black hole in spiral models developed by Luke Kelly. Basically we can't resolve any of these processes that drive binary in spiral in simulations, in these large scale cosmological simulations. Luke developed this subgrid model to track all of these processes for stellar and gas-driven evolution and ultimately gravitational wave-driven evolution of black hole binaries to predict the timescales for black holes to actually inspiral and merge. And that's very useful for making gravitational wave predictions, among other things. Now, my student Mohammed Sayeb, who graduated last year, used this to build a black hole spin evolution model for binaries as well. And what I want to highlight today is the work he's also done recently on black hole triple formation. So just to briefly outline how this works. So we're taking the binaries that have been identified in the illustrious simulation. So it's anytime a black hole merges in the simulation, and so we can trace its subgrid inspiral. And then we're looking at when that binary evolution process overlaps with another one. So we're treating them all in isolation, but in many cases, one binary has not actually finished merging before the next one forms, because these inspiral timescales can be many gigayear. And so we have analyzed this population and classified them, the ones where there's some overlap in that binary inspiral, into these three categories. One in which no triple system forms because the second binary just chases the first one all the way down, but the first one merges before the intruder gets there. And then these weak triples, as we're calling them, where the intruder does overtake the inner binary, but it does so at large separations of order 100 parsec or a kiloparsec. And then finally, the strong triples, where the intruder overtakes at small separations of a few parsec or tens of parsec. And so the former case, the weak triples, are those that are likely to be this type of system where we could have some interesting observational constraints, especially in the more local universe. This is an example of a triple AGN system that was discovered recently. And then the strong triples are these that would have potentially chaotic three-body interactions and could eject a black hole at high velocity from the system and could greatly, thank you, and could drive the inner binary to much more rapid merger. So that's very important for gravitational wave event rates and source populations, but also for the extent to which black holes are retained in galaxies and to which you might have multiple black holes in the same system at the same time. So we think a lot of the time about this in the context of stalled binaries of black holes that may stall at low redshift for long periods of time before merging and need a third black hole to come in to help them merge. But I just wanted to show this movie of an assembly galaxy at high redshift from the illustrious TNG50 simulation to highlight how dynamic these environments are at higher redshifts too. And of course, this is where the merger rate of galaxies is very high, as you have all of these streams of gas and clumps and proto-galaxies falling in continuously. So this is a very common scenario in the high redshift universe as well. And so, what we find is that there is actually a bimodal population of these triple systems. So first of all, they are very common. 35% of all binaries that form in illustrious overlap in time, according to our inspiral models. And 20% of all binaries, so the majority of those, do form triples. So at some point, the third black hole overtakes the inner binary. And 5% of them form strong triples. And you can see that it is this bimodal population, right? There's this separation between the strong and weak triples here. And we find that this is pretty insensitive to the binary inspiral model parameters. So this paper will be submitted very soon. And then the final seconds I have, I just wanted to very quickly highlight again, the talk about black hole seeding, this prescription for a hybrid semantic model where we can trace black hole seeding sites through the merger trees and TNG that Annalise will tell us more about in the next session. And then also the poster presentation by Akmat Bomek, where he is using constrained initial conditions in these Zoom cosmological simulations to produce black holes, massive black holes at Z of 6 through a combination of black hole mergers and accretion.
Many thanks, very useful results. We have a question already from Melanie, so I will give her the word. Yeah, please speak.
Hi, Laura. Super nice results. I was just wondering, those triple black holes, would they lead to a very large population of recoiling black holes or wandering black holes in galaxies? Yeah.
Yeah, no, that's a great question that I definitely want to get a more quantitative answer to. So I think it's not clear to what extent that's going to produce a population of recoiling black holes relative to, say, gravitational wave recoil. But certainly, yes, it will kick black holes out. It looks like about 5% or a few percent of all black hole binaries might form these strong triples. So, we're talking about a small fraction of all systems, but over time, of course, that could lead to a large population of wandering black holes.
Cool.
I just don't have any, more numbers to put on it right now.
Yeah, many thanks. I think we can then come to our next speaker. So this will be Wako Ishibashi.